The two main states of energy are called kinetic and potential energy. Have you heard these terms before?
Yes.
Kinetic energy and potential energy. Okay? This is the most common conversion of energy that happens, and it happens all the time. So a conversion of energy is when energy transforms from one type to another type. And this happens all the time, especially with movement and objects. We see a transfer from kinetic energy to potential energy, or potential energy to kinetic. We see this happen a lot. So we're going to kind of break down what do these two states of energy mean, right? What are they? What types of objects fall into each category? Can objects have both types? All those questions we're going to be able to answer, okay? So the two main states of energy are potential energy and kinetic energy, okay? Ooh, goodness. All right, the first thing we're going to talk about is their main definition, okay? Kinetic energy is any sort of energy of an object that's in motion, okay? So the prefix kina, have you heard that prefix? Where else have you seen that word before? Or kin? What other words do you see that prefix in? Yeah? Okay, yeah, that's right. The word kin means family, but where do you see this prefix? Kina.
The Christmas song.
No,
I mean so for real.
I don't know what you're talking about.
What's the one? No, hold on.
Okay, kinesiology is the study of muscles, movement, yes, all that kind of stuff, right? But kina means motion. Sorry, excuse me. Okay? Potential energy in its own category is considered stored energy. So this is energy reserves, right? Energy that's in reserve for us to be able to use. Okay? So let's talk about kinetic energy in a little bit more depth here. Kinetic energy is energy of an object that's in motion. So if an object is moving at all, it has to have kinetic energy. What's another way that we talk about, what's the word that we use to describe how fast we're going? Velocity. Good. So if an object has velocity, then we know it has kinetic energy. Okay? The faster an object moves, the more kinetic energy it has. Right? So velocity is a direct correlation to the amount of kinetic energy that we have. So if you have more velocity, that means more kinetic energy. Okay? So the faster an object is going. The greater that an object's mass is also has to do with its kinetic energy. So those are directly related. So the bigger and the faster something is, that means the more kinetic energy that it has. Okay? So those is dependent upon both of those factors, both mass and velocity. Okay, before we even get into much more of that, somebody raise their hand and remind me of the units for mass. What are the units that we use for mass? Raise your hand if you think you know. The unit. Yeah, Ava? No, for mass? Mass is how much something might weigh.
Grams?
Not grams. What is it, Jacob? It's got to be kilograms. Kilograms. Okay, the unit that we're going to use for mass is kilograms. That's the base unit for the metric system. Right? It's not the simple unit. Gram is the simple unit. But the most commonly used unit for mass in the metric system is kilograms. What should our unit for velocity be? Raise your hand if you know. Cora? No, not kilograms per second.
Wait. Oh my gosh, that's so
Meters per second. Meters per second, okay? Meters per second. Okay, so we have to make sure that when we plug things into our problems, our mass has to be in kilograms and our velocity has to be in meters per second, which means we might have to do some conversions to be able to put them into our problems. Okay, we've got to make sure that we know how to convert those things. If I needed to convert 4 grams to kilograms, how would I do it? Okay, I'm going to use a table, but what's my conversion factor? Do you remember? 4 grams. Grams goes on the bottom, kilograms goes on the top. But what are my numbers that have to help me convert here? Jacob, what are they?
1 and
Which one is which?
1 kg.
1 kilogram is equal to 1,000 grams. So we would divide we would divide by 1,000. So when we want to convert from grams to kilograms, we divide by 1,000, right? We multiply across the whole top, divide by the whole bottom. That should be a conversion that we feel comfortable with and that we can do quickly, okay? It should be one that we've done enough times. We should be able to know how to convert grams to kilograms quickly and easily, right? Divide by 1,000. Okay. So I want you to answer this question. Is it harder to get a big object moving or a small object? Let's say we've got a big boulder and a small rock, small stone. Which of those is harder to put into motion?
Big.
Big. Why is that?
It has more mass.
It has more mass, right? Let's answer the question in reverse, right? Is it harder to stop a big object or a small object?
Big one. Stop.
Which is it harder to stop, a big object or a small object?
Big.
A big object, right? It's the same principle. Listen. It's the same principle. This is called Newton's Law of Inertia. Have we talked about that word before? Have you heard that word? The Law of Inertia.
Is it like when you're in a car and you like stop and like your body moves forward?
Okay, very good. An object in motion stays in motion. An object at rest does what?
Stays
Stop.
at rest.
An object at rest
Stays
at rest. So that what that says is that inertia is basically an object's resistance to change. So like you're in the car, you've got your seatbelt on. The seatbelt is to keep you stopped if the car stops, right? If you're moving 45 miles an hour because your car is moving 45 miles an hour and your car stops, you want to keep moving forward, right? Your body resists change. So your seatbelt is there to keep you safe. Yes. Right? But the same thing works for starting and stopping big objects. It's really hard to get a big boulder into motion because that object resists change, right? That's what inertia is. Inertia has to deal with an object's mass, right? Mass is a measure almost of inertia. So the bigger an object is, the more likely it is to resist change. Boulder rolling down a hill. Easy to stop or hard to stop?
Hard.
Very hard to stop, right? It's in motion. It doesn't want to stop being in motion. Things like that, okay? You feel okay about that? All right. Here's our equation for kinetic energy. Here is our equation for kinetic energy. This is going to be an equation that we use really often. Okay? The equation is 1/2 times m times v squared. And I'm going to actually write it. I like to write my fraction like this. Kinetic energy equals 1/2 mv squared, right? It makes no difference how you write it. Full fraction, slash like that, it makes no difference. But that's how we're going to write that equation. This question underneath says, which has a greater effect? This should say on, sorry. Which has a greater effect on kinetic energy? Does mass affect kinetic energy more, or does velocity affect kinetic energy more?
Mass.
Okay, how many of you think mass? Raise your hand. How many think mass affects it more? How many of you think velocity affects it more? Can you give me a reason as to why? I would agree that velocity affects it more. Why would you say that?
Because it's the energy of motion.
No, not necessarily. I'm talking about just the equation. Why does it affect it more? Yeah.
Because you're squaring.
It's squared, right? My velocity is squared. So that number weighs more heavy on the amount of kinetic energy that's formed, okay? What I want us to do for this chapter is to start giving ourselves a little sheet of our equations, because we're going to get 2 or 3 equations for this chapter. And I want us to have them out and available for us to see, so we're not having to flip back through our notes all the time. So, potential energy is stored. Okay, it can be stored lots of different ways. It can be stored chemically in food, in an atom, in fuel that we use. It can be stored lots of different ways. But the potential energy that we're going to focus on is really a type called gravitational potential energy, which is energy stored in objects in their ability to fall. Okay, objects that have the ability or the capabilities to fall. Okay. So potential energy can have lots of different facets to it, but we're going to focus on gravitational potential energy, okay? It's dependent upon the height of the object. Dependent upon the height of the object. Okay, gravitational potential energy is dependent upon the height of the object. Okay, and the way we look at this is that if an object can fall and do work on another object, it has gravitational potential energy. Okay, and we sometimes abbreviate potential energy as P, E, and then you can put a little G by the end of it to say that it's gravitational potential energy. Okay, but I usually do use two capitals. I don't know why I didn't there. Okay? Just like kinetic energy was abbreviated. PE is potential energy, and then you might see a little G next to it so that it's gravitational potential energy. So I want you to think about this question here. Let's say this is the ground. I've got a nail sticking up out of the ground. Okay? And I've got two objects. An object that could fall from 3 meters and hit the nail, or an object that could fall from 100 meters and hit the nail. Which of them would do more damage to that nail when it hits it?
100
The 3 meters or 100 meters? The 100 meters. That object would fall and drive that nail further into the ground than the one that fell 3 meters. Would we all agree with that?
Yeah.
That's because this one has more potential energy, right? It has the ability to do more work on this nail, right? Work, remember, is applying a force that moves an object, right? That displaces an object. So if this object falls, it might like tamp the nail down a little bit. But if this one falls, it's probably driving it all the way into the ground. Would we agree? Right? So the greater off the ground an object is, the more potential energy it has. Okay? If you stand on a 3-meter diving board, you have 3 times more potential energy than if you were standing on a 1-meter diving board. That kind of answers the same question, right? Consider you're standing on, let's say this is the water now. Okay, here's your diving board. Here you are. Here's a higher diving board. Here you are. You probably need to stand on the board. Okay? When I dive into the water, I might go that far under, right? When I dive into the water here, I might go that far under, right? Do you see the difference? The more energy you have, the more you're going to make an impact when you get to that ground level. Okay? All right, so here's our equation for gravitational potential energy. Okay, it says the bigger they are, the harder they fall is not just a saying, it's actually true. It has to deal with both the mass of the object and how high it is off the ground. Okay, so here's our potential energy equation. M times G times H. Okay, M is the mass of the object. G is called the acceleration due to gravity. And we haven't talked a lot about gravity yet. Okay, but it has a value of 9.8. And then H is, of course, the height of the object. I want to review a few things here, especially with units, okay? This equation should go on your equation sheet, so you have it out to reference. Okay, this equation should go on your equation sheet under potential energy. Remind me one more time, what is the mass? What's the units for mass? Kilograms. The G value will always be equal to 9.8. Okay? This lowercase g is called the acceleration due to gravity. And we haven't talked a lot about it yet, but that value 9.8 is what the value of gravity is on the Earth's surface. So we're always going to plug in 9.8 here for g. Okay? And then the height of our object, what do you think the height should be measured in? Meters. It's got to be meters. Has to be meters. Bless you. Okay, it has to be meters. Okay, so in order for these objects, in order for our equation to work, we have to have things in the correct units. Okay, so meters is really, really important. What if my question said that my height was 17 centimeters? How would I convert from centimeters to meters? Okay, I'm going to make the table, but what am I going to end up dividing by? 100. How many centimeters are in a meter, right? There are 100. That's another conversion that we should feel super, super, super comfortable with, right? 17 divided by 100 is 0.17 meters. Okay, those are conversions that I think we need to be able to do quickly and without much thought by this point, right? We've done them enough that we can convert from grams to kilograms and centimeters to meters pretty quickly. How do we feel about that? Give me like a 5 out of 0 to 5. 5 is I know everything you're talking about. 1 means I don't even know what language you're talking. Okay, on your conversions. I don't care what your number is. I just want to see what it is. Okay, all right, we're halfway probably. Okay, all right, good. All right, the last type of energy that we're going to talk about is what's called elastic or spring potential energy. Okay, this is energy that's being stored in some sort of spring or coil. Okay, you know what I mean when I say spring or coil? Okay, you've got it probably in a pin that clicks, right? There's a spring that's in there. You've got springs that hold up your car, right, to make it ride smoother. There's springs in all sorts of toys. There's springs in rubber bands. What's the toy called? A slinky, right? That's a spring, even though it doesn't have a lot of spring to it, but it is a spring. Those are all examples of elastic or spring potential energy. Okay? What's it called when I push a spring together? What's that word called? What's it called? A compress, right? When I compress the spring. Then what's it called when I pull it apart? Expand or stretch. Those are both words that we need to be familiar with. The spring was compressed. That means I'm pushing it together. And the spring was stretched. Means I'm going to pull it out farther. So here's the equation for potential energy of a spring. Potential energy of a spring. 1/2 kx squared. So we're going to get 3 equations here for energy. 1/2 kx squared. This is potential energy of what? What's the S stand for?
Spring.
Spring. It stands for spring. Okay, and I want that equation to go on your equation sheet as well. Okay, K is something called the spring constant, and X is the distance that we've been stretched or compressed. Okay. What do you think? It needs to be measured in meters, right? It needs to be measured in meters. So we're going to have to convert that number a lot from centimeters to meters. Okay? So our units, do we feel comfortable with our units now and we know what things should be in? Right? So you have to make sure that as you're reading problems, if you see red flags of units that are not correct, we convert those first before we start doing the math that goes with it. Okay? Have we done squared numbers and square roots of things in algebra or pre-algebra? Some yes, some no. Okay, we're going to work through that. Let's go ahead and try our first problem here. So let's go to the next slide, and we're going to talk about doing the math now with kinetic energy problems, okay? This is going to feel very similar to the motion unit we just finished, right? Identifying what is our velocity, what is our mass, what is our all that stuff. Those are the things we're going to find, okay? So this first asks me how much kinetic energy. So kinetic energy is going to be my question mark, right? That's what I'm solving for. Okay, then it tells me I have a 0.450 kilogram baseball. What variable does that have to go with? It has to go with mass, right? Mass is equal to 0.450 kilograms. And then it tells me it's traveling 15 meters per second. What variable does that have to be? It has to be velocity, right? 15 meters per second. And so now I just need to go find my kinetic energy equation, right? We said the equation for kinetic energy is 1/2 mv squared. So don't I have my mass? And don't I have my velocity? Yes. So all I need to do is plug those numbers in. Okay, so let's go ahead and look at our problem. We're solving for KE, kinetic energy. We're going to take 1/2 times 0.450 times 15 squared. Okay, so let's take a look at our calculator. Do we know where the square button is? Do we know what squaring a number means? 15 squared means we're taking 15 times itself, right? You're taking the number times itself. So do you know where the squared button is on your calculator? I need everyone to have their calculators out. Do you see where the squared button is? Give me a yes, a head nod, or a no. I have no idea. Okay. Okay. Yep. X squared. So you can start with that if you want to. In my calculator, I would go 15 squared, and then I'd go ahead and hit enter. What does that give me? 225. Now, what do I want to do to that number? I still have to multiply it by both of those things, right? These are all multiplied together. So I'm going to take 225 and hit times. That automatically takes my answer. Times 0.5 times 450. No, times 0.450. Okay, and I get a kinetic energy value equal to 50.625. Okay, if you did not get that in your calculator, I need you to tell me so that I can help you work it out in your calculator. You could also just plug it in exactly that order. So you could take 0.5 times 0.450 times 15 squared, right? Your calculator should do order of operations correctly, which means what has to come first in order of operations? Exponents has to come first, right? Let's take a step back. It would be kilograms times meters squared over seconds squared. That's really ugly, okay? So what it's going to be instead is we abbreviate this unit to call it joules, and it's just a capital J. All of our energy is measured in joules. So all kinetic energy and potential energy will have the unit joules, and it's a capital J, okay? It's just an abbreviation of that unit, kilograms times meters squared over seconds squared. Okay, capiche? Okay, let's try another one. How much does an object weigh if it is traveling at 30 meters per second and has a kinetic energy of 4,300 joules? So we need to start writing out our variables first. Figure out what do these numbers in our problem mean, okay? I'm gonna leave the question at the beginning here, but let's say 30 meters per second. What's that have to be? Yep, just based on the units alone. We know velocity units are meters per second. So velocity is 30. And then what is this 4,300 joules? What's that equal? Kinetic energy equals 4,300 joules. Okay, so the question asks me, how much does it weigh? What variable does that mean I'm solving for? I'm solving for mass. Okay, when you get into real physics, we're going to understand there's a difference between mass and weight, but for right now, we're going to let it be. Okay, mass is going to be our question mark. I always want you to write out that list. I think it's really important, and make sure that we can see what variable are we solving for, right? My question mark is mass, so that's what I'm going to solve for. All right, my equation looks like this. Kinetic energy equals 1/2 mv squared. I'm solving for m. Okay, so let's put in my numbers of what I have. Kinetic energy is equal to 4,300 joules equals 1/2 times m times v squared. Okay, so we've got to do some algebra now to get m by itself. Our goal is to have m by itself. Would we agree there? Okay, so can we see what has to be the first step in my problem? Can you identify the first step? Okay, I'm going to do my exponent first. It doesn't really matter the order that this goes in. So we're going to have to get those things done. But let's go ahead and do 30 squared. All right, I'm just going to rewrite the rest of my problem. 4,300 equals 1/2 times m times, I'm going to plug in 30 squared in my calculator. And I get what? 900. Okay, so all I did so far is 30 squared. All of this right side of the equation is multiplied together. 1/2 times m times 900. So what do I need to do next? I need to multiply 1/2 times 900, right? Yeah. We agree? Yeah. It would just be like if it said 2 times x times 4, right? I would want to take my 2 and my 4 and I would want to multiply them together. So I'm going to do that. 900 times 0.5 gives me 450 still times m equals 4,300. Are we clear with how that math came through? Okay. What's my last step now? If I want to get m by itself. Divide by what? Divide this side by 450, and whatever I do on the left, I have to do on the right, or vice versa. Okay, so I'm going to take 4,300 divided by 450. That gives me a mass of 9.56. And then what would my units be that goes with that? No, for mass. What would my unit be for mass? Kilograms. Okay, for this chapter, I'm really going to put an emphasis on units. Can you put the correct unit with the answer, right? You need to make sure that we understand and think through what should our unit be, right? How do we measure mass? Tell me what questions we have about the algebra that goes with. Asks me, how fast is a 3,000 kilogram car moving if it has 53,000 joules of energy? Now, it doesn't even tell me what type of energy it is. It just says it has that much energy. Can you confidently say what type of energy it has? Kinetic. It's got to be kinetic because it's moving, right? So let's go and pick out our variables again, okay? 3,000 kilograms has to be mass. 53,000 joules has to be kinetic energy. And it says, how fast am I moving? So I have to be solving for velocity. All right, so I'm going to go plug those numbers into my equation now for kinetic energy. Kinetic energy equals 1/2 mv squared. So I'm going to put my numbers in. 53,000 equals 1/2 times m times v squared. So my goal is not to solve for v squared. My goal is to solve for v, right? For just velocity. So let's figure out how can I do that. I need to multiply those numbers together first. 1/2 times 3,000 gives me 1,500 times v squared. What's my next step? What does my next algebra step have to be? What do we think?
Divide by 1,500 on each side.
Good. Divide by 1,500 on each side, right? That cancels it over here. That gives me about 35.3 equals v squared. So am I done right there? No, what has to be my last step then? I need to take the square root. Do we understand what a square root is? A square root is reversing a square, right? So we're trying to find what times itself equals 35.3. Okay, and we do that in our calculator by taking the second button. Some of you don't, maybe some of you don't need a second button here, but I would need to take second square, which gives me the square root symbol, 35.3. And I get a value of 5.94. So that means my velocity is equal to 5.94. And what would my units be? Meters per second. Okay, so I want to come around and check to make a boy's holding a ball on a 30-meter clip. If the ball has a mass of 7.5 kilograms, how much potential energy is stored in the ball? Okay, so it tells us we're looking at potential energy. Do you think we're going to use potential energy of gravity or potential energy of a spring here? I'm going to use gravitational because it's not a spring, right? It's just an object that's being held high off the ground. So we've got 30 meters. What variable does that have to associate with? Height, good. So height is equal to 30 meters. It says the ball has a mass of 7.5 kilograms. It says how much potential energy. Okay, so that's what I'm solving for. How much potential energy? So my equation for potential energy of gravity is mgh. Do I need to get the g variable? Does that come from my question?
Yeah.
What's g always equal to? Always 9.8. As long as we're on the surface of the earth, it's equal to 9.8. Okay, so I'm solving for potential energy. I'm going to keep that there. My mass is equal to 7.5. G, we said, is equal to 9.8. and my height is equal to 30. Okay, so now we're just really simple algebra. All we have to do is multiply those things together. Let me ask you this question. Does it matter the order in which you multiply those together in your calculator?
No.
No, right? It makes no difference. Okay? So if I plug all those in, multiply them together, it gives me what value?
2,205.
Good. And what would my units be since it's energy? What would my units be for energy? We said both types of energy are joules. Yep, capital J, which stands for joules. We need to make sure when we speak it, we say the whole word, right? When we write it, it's just the abbreviation. But when we speak it, it's good practice for us to say what that unit is. Okay? This algebra is a lot simpler, right? It's just multiply, multiply, multiply. There's no square, square root, or anything like that. I want you to try the next one on your own. Next one on your own. What is the mass of an object that is 45 meters off the ground with 90 joules of gravitational potential energy? Okay, so it's asking us what is the mass. That means that's got to be my question mark. It says our object is 45 meters off the ground. So what variable does that have to apply to? Height, good, 45 meters. It says it has 90 joules of gravitational potential energy. So I'll plug that into my equation. Right? You don't have to write it out like that if you don't want to. I just want to do it so that we see it several times, right? And we feel comfortable with that. 90 joules is equal to mass times G, which we said is always 9.8 times the height. All right, so I'm going to multiply these two together first. That gives me 90 joules equals mass times 441. Then I'll divide over 441 on both sides. That gives me a mass equal to what? 0.204. Good. And what would my unit be that goes with mass? Kilograms. Very good. Very good. Okay, do we feel like pros by this point?
Yes, I'm a pro.
We're a pro. We're ready to go. Okay, we're getting close. Are you getting close to being a pro? Like a semi-pro? All right, this says a spring with a spring constant of 400 Newton meters is compressed 6 centimeters. How much energy is stored in the spring? So the fact that it says spring, we know we're going to use a different equation this time. We're going to use the potential energy of a spring, which is equal to 1/2 kx squared. 1/2 kx squared. That's the equation for springs, right? Don't you have that on your equation sheet? Yes. Give me a confident yes.
Yes.
Yes. There we go. I love it. Confident yes. It's on our equation sheet. We're ready to go. Okay. It says our spring constant is equal to 400. So K is equal to 400. And it's compressed 6 centimeters. How do we feel about that?
It goes on the X, right?
Okay. It goes with X.
You're going to have to make it into meters.
Bingo. We got to make it into meters. How many of you were thinking that you just didn't want to say it? Oh, yeah, we need to be thinking that, right? Centimeters is a red flag, so we got to convert that to meters, okay? So 6 centimeters. How do we divide by, what do we divide by to get it to meters? 100, right? 100 centimeters is 1 meter. So that means it becomes 0.06 meters. Okay, and it's asking us for potential energy. Okay. Let's take a look. We're going to plug it in here. Potential energy is equal to 1/2 times K times 0.06 squared. Okay. What's 1/2 in your calculator? What are we going to put that in as? 0.5. Good. Times 400 times 0.06 squared. Okay. And that gives me a potential energy equal to a pretty small number. We're going to get a pretty small number of potential energy. What'd you get?
120?
No.
100.
Oh, wait, I didn't square. I didn't square.
No.
Calm down.
I haven't heard what I'm looking for yet.
Calm down, Cora.
I got about 0.72 joules.
Yeah, point